Hi everybody, this is Cal with section 3.2 limit theorems and 3.3 whose name I can't remember at the moment. Limit theorems, we're going to develop a number of theorems about limits that let us evaluate limits and prove limits more easily. To start with, we have a definition of what it means for a sequence to be bounded. It's very similar to what it means for a set to be bounded. This is a definition that you should know and understand pretty easily. 3.2.2 is a pretty important theorem. Any convergent sequence of real numbers must be bounded. Make sure you understand the proof of this. This is a pretty easy proof, the remark below it is really useful as to why it should hold. Below that remark, we go into a discussion of sums, differences, products, multiples, quotients of sequences. Hopefully it's relatively straightforward what they mean by those things. And 3.2.3 is a theorem about them. It says, for instance, that the limit of a sum of sequences is the sum of limits, exactly how you would expect it to be, and so on. They separate out quotients to part B because they need the bottom thing to be non-zero. They just have an extra hypothesis there. Work through a couple of the proofs here, especially in part A. These are all proofs that you should be able to do on your own, and I would say that any one of them is probably fair game for a quiz or test situation. So make sure you understand the logic behind why theorem 3.2.3 works. There's a nice comment after the proof ends in the middle of 65 about how you can extend these results to a finite number of convergent sequences instead of just a sum of two of them, and so on. And I would say you should try to prove these assertions by induction on the number of sequences involved. In theorem 3.2.4, we say that if we have a convergent sequence of real numbers that are all bigger than or equal to 0, then their limit is bigger than or equal to 0. That should be obvious. Make sure you understand the proof. 3.2.5 extends this to a comparison between two sequences. If one sequence is less than another, then the limit of the first is less than the limit of the second. And again, the proof is pretty easy. And finally, 3.2.6 says that if a sequence is bounded between two numbers, then its limit must be bounded between those numbers. Note, by the way, that this theorem only works if you've less than or equal to. If it was just less than, it wouldn't work anymore. So be aware of that. And this also leads us to the squeeze theorem, which is a direct, basically a direct application of 3.2.6. And the squeeze theorem should be familiar to most of you. And again, the proofs of all these are pretty simple, so make sure that you're able to follow them and maybe reproduce them. Yeah, I might even go as far as to say that you should try to prove these yourself before reading the proofs. The remark after the proof of 3.2.7 is pretty good, and any of these theorems can be weakened just to apply to the tail of a sequence. So we only need to say, for instance, in the squeeze theorem, that xn is ultimately less than or equal to yn is ultimately less than or equal to zn, and so on. There's a lot of really good examples in 3.2.8. We've already done in class something like example A, but make sure that you're able to follow it. Example B is even closer to something we've done. And the rest of these examples are all pretty good. I suggest that you read them carefully and understand how they all work. Be able to do similar things if you change the numbers, that sort of thing. Starting from 3.2.9, we have a number of just kind of utility theorems about sequences. The first is that if a sequence converges, its absolute value converges to the absolute value of the limit of the original sequence. Then we have a similar thing about square roots. Then we have an interesting, kind of a ratio test sort of looking thing for theorem 3.2.11. That one's a little bit cooler. The proof is a little more convoluted, so that might be a good one to pay some attention to. And there's an illustration of its use right after the proof of the theorem. And that's section 3.2. Moving right along to section 3.3, monotone sequences. This is a pretty important section and pretty generally useful. So we start with a recap of what we know so far, the different methods that we have to show that a sequence converges. And the thing that all these methods have in common is that we need to at least suspect what the value of the limit is before we use these. We are not always going to know what a sequence converges to when we want to prove that it converges. So what this section deals with is a way to get at convergence of a sequence without knowing what it converges to before proving it. I absolutely want you to come into class the day this is due knowing definition 331. I want you to know what it means for a sequence to be increasing, decreasing, or monotone, meaning it's either increasing or decreasing. It's either always going up or always going down. And then there's the monotone convergence theorem, 332. This tells us not only is any bounded monotone sequence convergent, it tells us what it converges to, which is nice. But somehow the important part of this is that it must be convergent. The proof here is pretty important. I would suggest that you do your best to understand how it works. And again, it's a proof that you probably could come up with yourself if you wanted to. So, going on, we have a number of examples in 333, and these are useful ways to use the monotone convergence theorem. Then we have an interesting little bit about inductive sequences and how the monotone convergence theorem can be useful for some of those. I really like example 334A and B for that matter. These are both pretty useful, and you should be able to do problems like these by the time we're done covering this section. The last couple of examples in the section are a little bit tougher. The first is calculation of square roots by approximating it with a sequence. That's a relatively accessible example. I suggest maybe you try it out for a equals 2. Try approximating the square root of 2 in this way. Then we have an example dealing with the number e, which is a cool example. I know that it's a little bit hard to follow. If we have time, I'll go over it in class. No promises, of course, but it is a cool example. And that kind of ties together the section. So, see you later.